Hello Internet, Jonathan Toomim here. Today I'm going to be talking about Bitcoin Cash's difficulty adjustment algorithm, how it's broken, why that matters, and how we can fix it. The purpose of a difficulty adjustment algorithm for Bitcoin Cash is twofold. First, it needs to maintain blocks at 10 minutes per block, but second, it needs to keep the hash rate and the profitability balanced between Bitcoin Cash mining and BTC, Bitcoin Core mining. It does this by measuring hash rate as quickly as possible and then updating the difficulty so that if the hash rate is too high and the blocks are coming too fast, the difficulty goes up, which makes it less profitable to mine and chases hash rate away. Ultimately, this is supposed to result in hash rate reaching an equilibrium where it's equally profitable to mine BTC and BCH. Unfortunately, the initial attempt at doing this didn't work that well, and so we got these crazy oscillations in confirmation times where it was taking 40 minutes or a few hours for some periods of time before a transaction would get mined into a block. On November 13th, we instituted a new difficulty adjustment algorithm that was a lot more responsive and based on a 144 block one-day window instead of a 2016 two-week window, and that improved things a lot, and confirmation times mostly went back down to around 10 minutes. Unfortunately, they didn't stay there, and in recent years we've seen confirmation times creep up, and especially like last month in January 2020, we saw confirmation times get up to about 28-29 minutes on a 2-week interval on average. That's almost 3 times as long as it's supposed to take for a transaction confirmation. Bitcoin Cash is supposed to be an internet money that is fast, cheap, reliable, and censorship resistant. And this problem with the difficulty adjustment algorithm is making it so that transactions, they're still cheap, but they're not fast and they're not reliable. It also challenges the censorship resistance because this difficulty adjustment algorithm bug compromises the security model of Bitcoin because it changes the mining incentives in some potentially nasty ways. So I wanted to understand why this was happening and what we could do to fix it and prevent it from happening in the future. And to do that, I put together this simulation tool. So I went and took some code from QPChan, from Neil Booth's simulator for difficulty adjustment algorithms, and built a UI on top of it and fixed a few bugs and some other stuff. So I'm going to walk you through how difficulty adjustment algorithms work and also how this particular tool works, and use this to show some interesting information about what's probably going on. First of all, so we've got a few different graphs, and we've got different algorithms, different difficulty adjustment algorithms being graphed in each one of these graphs. You can see that there's something going kind of wonky with this CW144 algorithm. And that's interesting and all, but right now it's just a distraction, so I'm going to turn it off and switch over to a variant of this WTAMA algorithm with a slower responsiveness and smoother response. So the way this simulation works is it's trying to simulate the hash rate switching incentive between Bitcoin and Bitcoin Cash. So we've got some parameters. We've got the initial exchange rate between the two currencies, fees, and some other stuff, the number of blocks that we're simulating. And we've got 3 different types of miners following different strategies. We've got consistent miners who always mine Bitcoin Cash no matter what at some hash rate. We've got greedy miners who will switch all of their hash rate over to mining Bitcoin Cash as soon as it's more than X% more profitable to mine Bitcoin Cash than Bitcoin Core over a 1-block window. Currently have this set to 0 because the greedy miners, they make the graphs a little bit harder to read and make them more jagged. So, and they're a little bit less friendly. And in this simulation, I wanted to make things as friendly as possible. And then lastly, we've got the variable miners. And the variable miners tried to split their hash rate between the two chains in a way to bring the profitability towards 1.0. So they will move to the more profitable chain, but they won't do so all at once. They'll do so in a proportional, smooth fashion. They've also got this memory term, so if they don't quite achieve perfect parity, next block they'll try a little bit harder. Um, so I'm going to actually change the number of blocks in this simulation to be, let's do 50,000. So that'll just give us a little bit better of a view, a longer term view. That's basically 1 year. By the way, this tool will be available on the internet. I'm going to put a live version on my website and put the URL for how to access that down below. That version will not allow you to do long block intervals because it puts a lot of load on the server and there's a lot of data that has to be sent over. So if you want to do these long simulations, high resolution simulations, you should download the source code from my GitHub and run it locally, and then you'll be able to get these kinds of graphs. Okay, so now let's take a look at what kinds of graphs we've got. We've got the difficulty graph. It's pretty straightforward. We've got a hash rate graph, and then we've got this revenue ratio and exchange rate graph, and we've got a few other things down below that are less important. So let's start with the revenue ratio. So this black line right here is the exchange rate, and this simulation will vary the exchange rate every block by a small amount, and then around 10 times per simulation, it will also make these rapid jumps that increase the exchange rate by either 10% or 15% or decrease it over the course of a single block. And these are intended to stress the difficulty adjustment algorithm and see how it responds to these rare extreme events. So yeah, we've got this line 1.0 is right here. And the goal for all of these difficulty adjustment algorithms is to keep the revenue ratio as close to that as possible. And you can see that the two algorithms that we have different performance. The blue one isn't quite as close to that 1.0 line as the orange one most of the time, but every now and then when the exchange rate changes, the blue line returns faster. Basically what we have is responsiveness versus precision. The blue line is more responsive but less precise. That's a pretty common trade-off that you see in a lot of different types of difficulty adjustment algorithms. So when the exchange rate goes up, profitability goes up for a short period of time, and that causes hash rate to go up. And so if we look here, we see the hash rate spikes. And it does that for both the blue line and for the orange line. The slower algorithm sees higher spikes than the fast algorithm. We then also see that the difficulty increases. By the way, there's a bit of an overshoot here with the orange line. That's actually not because of the orange difficulty adjustment algorithm, that's actually because of the miner behavior, and it's a little quirk that we've got there, but whatever. But yeah, so overall what we see is about what you'd expect. When the price goes up, the hash rate goes up, and then the difficulty goes up. When the price goes down, hash rate goes down, difficulty goes down. So this is working basically as intended. There are some things that are imperfect, like for example right here, during this downward price adjustment, especially in the orange line, but also in the blue line, you can see that all of the variable miners shut off their hash rate for, this is actually almost a day, and in the blue line, about 6 hours, something like that. So when it's less profitable to mine BCH than BTC, in a world filled with nothing but rational miners, the hashing would completely stop and the chain would stagnate. This is one of the chronic problems, one of the hardest things to solve with difficulty adjustment algorithms. Fortunately, in the real world, we have more than 300 petahashes of constant miner hash rate. It's actually about 2 exahashes, 2,000 petahashes, 2,500, something like that. So this problem isn't as severe as in the real world as it's shown here. But it does still exist, and it's something to keep in mind. So having an algorithm that adjusts quickly reduces the likelihood of these stalls or these slow periods in which we get very few blocks. The reason that we get these long periods of very few blocks is that the difficulty adjustment algorithm can't work if it doesn't have any data to work with. And if no blocks are being mined, there's no data, there's no information that the Bitcoin system can use in order to figure out what the actual hash rate is. So that's why it takes so long. There's a class of algorithms that solve this problem called real-time targeting algorithms, or tail removal algorithms. And the way that they solve this is by looking at how long it's taking for the current block to be mined. So like while miners are trying to hash and find a block, the block template has a timestamp, and as that timestamp changes, the difficulty of the block as it's being mined can change. And this does completely solve this problem, but it has a lot of other implications that might compromise the security. So it's not clear that that's a good idea. It's an interesting idea, and it's one that we should look at, but it's likely to be more trouble than it's worth. One last thing that we can see is confirmation times. And you can see that both of these algorithms stay pretty close to 10 minutes most of the time. Let's just zoom in a bit. They average a little bit above that. It's about 11 minutes or so. The slower algorithm is a little bit faster most of the time, except when those adjustments happen, when the price drops. During those cases, the slow responding algorithm does have larger and longer periods of slower confirmation. And that's pretty much as we'd expect. We can also look at the profitability of different mining strategies, and we can see that, yeah, it's better to be greedy. It's also better to be variable than greedy. Better to be variable than steady. But the differences are pretty small. So this is an example of successful regulation of profitability. Now let's go back to that other algorithm that we saw earlier and see what happens when things go wrong. So there are three things that we can learn from this algorithm, this CW algorithm, that are kind of interesting. One, we can see how things go wrong when they go wrong. Two, because we can see that things only go wrong for this algorithm and not for others, we can see that the problems with the algorithm, it's not that miners are gaming the system, it's that this algorithm has inherent problems. And then the third thing that is interesting about this is this like oscillatory behavior that we're seeing. It's really interesting because this CW144 algorithm is Bitcoin Cash's current difficulty adjustment algorithm. So all the problems that we're seeing are actually problems inherent to Bitcoin Cash's current DAA. So what's going on? So point number one, we can learn something by looking at exactly what's going on. So we're seeing oscillations in difficulty. We're also seeing oscillations in hash rate. And the hash rate goes down until only the steady miners are mining, and it goes up until pretty much all the variable miners are mining. We also see oscillations in profitability. So profitability is above 1, encouraging miners to come to Bitcoin Cash for maybe 80 blocks in a row, maybe 100 blocks. And then it drops, and it's below parity. Miners leave Bitcoin Cash for another 40 blocks, and then that repeats. By the way, the graph for the revenue ratio has a different x-axis scale than the graph for the hash rate and the difficulty. The revenue ratio is using block height as the x-axis, whereas the hash rate and difficulty graphs are using the timestamps, the days since the start of mining for the scale. One of the reasons that this matters is because what we see here, this period of long hash rate, there are very few blocks mined during that period. So even though these are longer in time terms, they're shorter in the number of blocks. So this long period here actually corresponds to this short period here. And then this short period here of high hash rate corresponds to this long period of a lot of blocks mined at a moderate profitability advantage. In this case, it's about 9% or 2%, somewhere between 2% and 10% more profitable to mine Bitcoin Cash. So that makes 5 exahashes of hash rate jump over to mining Bitcoin Cash for a short period of time, and then it mines maybe 80 blocks in a couple hours, and then it goes back to being less profitable. Hash rate drops to 0.3 exahashes, and then the next 50 blocks take another 15 hours or something like that, and it repeats. We can also see that this pattern, the timing of this, is very consistent. So we've got 177.2 days here, then 178.3, 179.38, 180.6, 181.7. So each time it's slightly more than 1 day from peak to peak, or from one feature to the next feature. And that ends up being very important, and we'll see why we get that pattern very soon. We can also see that user experience suffers dramatically as a result of these hash rate oscillations. Confirmation times average around 20 minutes in this simulation, and sometimes they get up to 40 minutes. Much longer confirmation times with this CW algorithm than with the WTAMA algorithms. We can also see that we get a lot of shorter blocks, with block intervals less than 100 seconds with this algorithm. And we also get, let me zoom out a little bit, a lot of blocks with very long intervals. These are block intervals of at least an hour, and CW144 gets about 6 times as many as WTAMA in these scenarios. So that sucks. That's unfortunate behavior, but it's important to remember that this is just a simulation, and just because we see it in the simulation with like this type of minor behavior doesn't mean that we see it in reality. So let's go over to Bitcoin Cash's actual hash rate statistics and see if we can find evidence of these oscillations. So if you go to most block explorers or look at most charts, you'll see something like this for the hash rate graph. And if you look at this, there doesn't really seem to be that much oscillation. There's some random variation, but that's just statistical noise, and that happens no matter what. That also happened with Bitcoin at the same time. For example, if we look at the Bitcoin graph, yeah, there's some random variation there. It's not oscillation. It's not regular, and it's only like plus or minus 10%. If we zoom in, we see basically the same thing. And the reason that we don't see these oscillations is because this graph, only gives us 1 day resolution. And the oscillations happen with a period of 1 day. So you're not going to see an oscillation that goes from up or top to bottom and then back to top in the period of 1 day if you're only getting one data point for that entire period. Because of this, I had to build my own tool for measuring hash rate, or for estimating hash rate with higher resolution. That's what this is. By the way, you can all go here and play with this yourself. So if we look at the Bitcoin era, you get this noisy estimate, varies by plus or minus 30%, but there's no like periodicity, there's no pattern, it's just random white noise. If you instead look at this recent time in Bitcoin Cash's history, you see something very different. You see very clear periodic activity with a very high amplitude. So in this period, hash rate was oscillating between around 2 exahashes, 2.3 exahashes, all the way up to 24 exahashes. That's a 10-fold swing in hash rate. The period of this was approximately 1 day. So we went from January 18th to January 19th, January 20th, 21st, 22nd. It's about 1 day plus 1 hour, one day plus half an hour, something like that. So again, slightly more than 1 day. This is the same pattern that we saw in the difficulty simulations. And if we look here, we can actually see that the difficulty in this red line is going low at the same time that the hash rate is going up, and vice versa. So we're also seeing that we're seeing evidence that these oscillations in hash rate are being driven by miners switching to the most profitable chain, and that in turn is driving the oscillations in difficulty, which determines the profitability. So that month of January was much worse than usual, but these oscillations have actually been going on for a really long time. Like, as far as you go back, you're just going to keep seeing the oscillations, because the oscillations have actually always been here with this algorithm. Anytime you look after the DAA was forked in, you'll see those oscillations. So on November 13th was when the DAA started. And then again, you see those oscillations. They're not as large in amplitude then as they are now because fewer miners were doing the switch mining, but it was still happening. So this gives very strong evidence that the Bitcoin Cash DAA is inherently oscillatory. Let's just zoom in on this so you can get an idea for the regularity here. Right? So we've got, again, October 17th, October 8th, oh, this is going to October 19th, so October 20th, 21st. You also sometimes see patterns where you get actually 2 oscillations per day. There's a second resonance going on here, but it's still basically the same thing going on. And we'll understand why we get this oscillation in a second. So I'd like to now explain how the DAA works. The DAA is based on a simple moving average of hash rate estimates. Basically, you can estimate the hash rate at any given block by taking how long it took to mine that block times the difficulty times some constant. So the harder it is to mine the block, the more hashes it takes to mine that block. For any given difficulty, there's a certain number of hashes that it should take as an expected value. And so you can estimate what the current hash rate is by calculating what that the expected value is. Of course, if you just look at one point, you're not going to get a very accurate estimate because there's a lot of luck involved. So what you can do is, instead of looking at one single point of how long it took to mine that block, you can look at many different points. You can take maybe 144 or 2016 different block intervals, add them all together, and divide by the number of blocks that were mined, and that can tell you what the number of blocks per hour was and whether the difficulty is too low or too high. Graphically, you can describe this as as taking 2 blocks, like this block right here and this block right here, for example, and drawing a line between those 2 blocks. And if that slope is more than 10 minutes per block, that means that the difficulty is too high and it needs to be adjusted downward. If the slope is less than 10 minutes per block, that means it's too low and needs to be adjusted upward. So let's just take a look at this graph. This is, again, the block height versus date. I'm just using markers instead of the line graph. And this is actual data from Bitcoin Cash from January 10th. And Bitcoin Cash uses a 144 block window. So if we look at this block, 617.149 plus 144, that's something like this block right here. 149 plus 144 is 295, so this is 298. So this is ever so slightly larger. This screen window is ever so slightly larger than Bitcoin Cash's difficulty adjustment algorithm window. So if the difficulty were correct and the hash rate were correct for that difficulty, we should see a line from this bottom left corner up to this top right corner. And if it's too shallow, then that means that we weren't mining blocks fast enough. It was taking too much time, and we weren't getting enough blocks, and so the difficulty needs to be lowered. If it's going too steep, and if it's hitting up here instead of at the corner, that means that difficulty is too high and the difficulty needs to be lowered. If you look at the blocks, you can also see that this is a very short time period in which many blocks were mined. It looks like about 16 or 15 blocks in half an hour or 15 minutes. And these periods where you've got a long distance between blocks, that means that the hash rate is low and blocks are taking longer than they should. And so you can see here, high hash rate, low hash rate. And this gives us some very interesting view into how the algorithm works. You usually think about when blocks enter the window and how that affects the difficulty. So as we go through and change and bring these blocks into the window, that makes the line a little bit steeper and makes it so that the difficulty adjustment algorithm sees that the hash rate is too high and needs to be adjusted downward. So that works properly. That's a negative feedback system. That means that when hash rate is high, profitability is made to go down by the difficulty adjustment algorithm, which makes hash rate drop. Negative feedback works as intended. But there's more to this algorithm than just blocks entering window. There's also blocks leaving the window, and that's where the problem occurs. So as a block leaves the window, that provides a system for positive feedback. When a block that took a very short period of time to mine leaves the window, that means high hash rate. When that high hash rate leaves the window, that makes the remainder show less hash rate, which increases the profitability by decreasing the difficulty. So that positive feedback means that when a burst of high hash rate blocks leaves the window, the difficulty goes down, and the blocks that are mined immediately afterwards end up being a high hash rate, low difficulty burst. This causes an echo. This causes a repeat of whatever happened 145 blocks ago to happen in the next blocks. And I'll just scroll through this and you'll be able to see that this happens over and over pretty reliably. Not perfectly reliably because there's still some chance involved, but this is basically the problem. So we've got some slow blocks. There's the slow blocks, and just keep your eye in this corner and in this corner. So we've got more slow blocks coming, and then all of a sudden we get a burst of high hash rate blocks. Boom. Then a little bit of slowness, and then more high hash rate blocks. Boom. And by the way, I haven't memorized this section. This is just, you can see, you can do the prediction yourself. Slow blocks, then high hash rate. Boom. Slow blocks, high hash rate. Boom. So yeah, this is the problem. This is what we need to fix. We need to fix the positive feedback that occurs with a delay of the window size when blocks leave the window. Now, we can think about this problem in a different way too. Instead of using this diagram of block times or block block height versus time, we can think of this in terms of filter theory. And let's go. Let's see. So a filter. There we go. So a filter works by taking some input signal and producing an output signal. The input signal is assumed to have some noise that you want to eliminate and produce an output signal that is cleaner. Filters are often described in terms of the impulse response as well as the step response. So for the step response, if we had, for example, an input that was 0 until time 0, and then 1 after that, what would the filter output be? For a simple moving average, if the window size is here, if this is 144 blocks, then our output would be 0 until that starting point t0, and then after all of this elevated 1.0 red was in the window, we would see that the output would also be 0 because we'd be averaging just ones together. And in between, we would be scaling linearly because the farther to the right we go, the greater the percent of blocks are high versus low, and it ends up being perfectly linear. And so this seems like a decent way of filtering out noise. If we look at the impulse response, on the other hand, we can see how the problem occurs. So an impulse response function will look at the output if you have an input that is 0, then 1 for a single data point, and then 0 again. So if this is our input for a simple moving average, the output will look like this. It'll be 0 until that point, and it'll go up by a small amount and stay high by that small amount for the entire window, and then go straight back to 0 again. And if I had drawn this to scale, the area under this red curve would actually be identical to the area under this this green curve, but that would have been really hard to see if I had drawn it that way, so I didn't. And the reason that we're getting this problem is because we get the negative feedback, which enhances stability of the system at time equals 0, and then this positive feedback at time equals 144 or 145, 146 blocks. And so it's this steep, concentrated downward movement that we want to get rid of. How can we do that? Well, there's actually some alternatives to the simple moving average. In filter communities, like the simple moving average is a very obvious thing to try, and so a lot of people try it first, and then they say, okay, this works well enough, and they stay with it. That's what Satoshi did. That's what a lot of people in like finance have been doing. But it turns out that if you want to estimate some changing function, the simple moving average is actually a really bad choice. If you think about it this way, the most recent block contains a lot more information about the current hash rate than a block, say, a day ago or a month ago. So if you want to try to take a bunch of blocks together and take their intervals and their estimated hash rates and use them to estimate the current hash rate, you should be giving more weight to the recent ones than to the old ones. If you're looking at the old ones, those will add some precision to your estimate, but they'll have lower accuracy because chances are the hash rate was different then, so we'll be estimating a different variable than the one that you actually want. So we can account for this effect of the recent blocks having more information by weighting recent blocks more heavily. So the one example function, popular function, is the linearly weighted moving average. And with a linearly weighted moving average, you have the most recent blocks weighted most heavily, and the most distant blocks weighted least heavily, and you linearly interpolate between them. So you end up with something that goes twice as steep for block 1, and then ends at 0 at the end of the window. So it looks like that. So the area under this blue line should be the same as the area under the green line, but and you get twice as much positive feedback, twice as much negative feedback initially. So the stability and like the responsiveness is doubled, and the positive feedback, the echoing producing force, is distributed over the entire interval, which means that you don't get those concentrated echoes. You don't get that resonance and that oscillation with the linearly weighted moving average that you get with the simple moving average. Another curve or another algorithm that you can use for doing this is called the exponential moving average, and that looks a lot like the linearly weighted moving average, but instead of decreasing linearly, the curve will decrease exponentially. And let's see, yeah, whatever. This isn't the best color to use, but that's what I have. So it goes up to basically the same level initially, but instead of decreasing linearly, it decreases exponentially. And because it's exponential, it never actually reaches 0. It just keeps going and going and going and going, and it gets closer to 0 as time goes on, but it never gets there. So with the exponentially weighted moving average, all of the blocks in the entire history get weighted in, and the really old ones have a very small role to play on the current difficulty, and the recent blocks have a larger role to play, but they all go into it, and that helps, in theory, that helps enhance the precision and makes better use of the information that's available. Because, you know, like a block that was 2 years ago, how long it took to be mined, that doesn't contain a 0 amount of information. It doesn't contain very much, but it's slightly more than 0. And the exponential moving average takes advantage of that. But of course, there's the obvious objection. If you want to be calculating this in real time, if you want to be actually calculating the exponential moving average, it would be rather inconvenient if you had to read every block header ever made. If you had to read an infinite number of block headers, that would just like be computationally prohibitive. So that kind of sucks. But we can go back to the drawing board a little bit and think this over, and maybe we can come up with another type of filter that's very easy to compute, but also gives good sensitivity and eliminates this concentrated positive feedback problem. So let's say we've got some function e, which estimates the current hash rate, and that function takes the current block's timestamp, the previous block's timestamp, and the current diff, and it gives us the new difficulty, or like the difficulty that this current block should have had in order to reach equilibrium. This would work really well if it weren't for the fact that mining is a random process. If mining were deterministic, this would be all we need. Unfortunately, mining is random, and the vast majority of the variation in the output of this function would just be statistical noise. So we need to do something to filter that noise and to minimize the effect that any one block has. One way that we can do this is we can take the estimate from the current block and mix it in with our old estimate from the previous block. So the old difficulty plus the new difficulty, let's just do this, and then divide by 2. If we take the simple average of those two, that would be a less variable estimate of the intended new difficulty. Of course, it's still too sensitive to the variation, the statistical variation, because like mixing it 1-to-1 with the old difficulty isn't quite enough. So instead of doing it 1-to-1, we can do it at some ratio. Let's say we say alpha equals 0.01, and we take old diff, let's say new equals old diff times 1 minus alpha. In other words, 99% of the old diff plus alpha times e to the that way, the new block is only going to change the new difficulty by like 1% either way. That makes the statistical variation much smaller. It's still pretty responsive. If you had a step, it would take 100 blocks or so for most of the adjustment to happen. But it balances those two things. So if we then try to calculate what the impulse response would be for this, or let's draw it out graphically, it would look something like this. So we let's do the blue. So the initial block is going to increase the difficulty by 1%. Let's just draw this as 1%. And then the block after that, let's go back to here. So the block after that is going to have that effect times 0.99. So the next one is going to be 0.99 of that, and one after that is going to be 0.99 of that, or 0.981 total, and then one after that is going to be 0.99 of that, or 0.972 or whatever, something like that. And basically each block is going to be weighted, I should have drawn this down here, but each block is weighted, or each block's impulse response is going to be 0.99 to the n, where n is the block number. And if you think about that, that's just an exponential decay function. You get x, which would be f of x roughly equal to 1.01 to the negative x, which is basically the same as e to the negative x times some constants divided by whatever. So yeah, it turns out that this extremely simple 2-tap filter that we wrote is the exponential moving average. And that's really cool. That means that Unlike the linear moving average, which requires us to do n taps, if we're doing a 144, I should not use yellow, that's not easy to see. If we're doing a 144 block moving average, a linearly weighted moving average would require us to examine 144 blocks. But for the exponential weighted moving average, regardless of what the time constant is, even if it goes out into infinity, we only need to do 2 taps. There's also some really interesting math that you can do with the exponentially weighted moving average that shows that you don't even need to use the last 2 blocks. You can actually use any 2 blocks, current block and any other block. And based on those 2 blocks, you can infer what the difficulty should be for the current block given its height and timestamp. Or you can figure out what the timestamp should be given its height and difficulty or anything else. And those 2 blocks can be the original fork block at which the new algorithm started, or it can be any other block. So this makes the exponential moving average is an absolutely scheduled difficulty adjustment algorithm. If you know what the difficulty is and you know what the height is, you can determine the timestamp. That means that if you're trying to do some mining shenanigans and mine a bunch of blocks really quickly and then mine a bunch of other blocks slowly in order to manipulate the difficulty and mine more blocks that than you're supposed to be able to in that time, you're not going to succeed because the difficulty scheduling algorithm is absolute. It doesn't matter what the path is, all that matters is where you end up. That makes the exponential moving average provable as being resistant to a lot of different types of hash rate manipulation, timestamp manipulation attacks. I think that's pretty cool. By the way, this is based on some research of Mark Lunderberg, who annoyingly has not published this research. So if you ever want to hear more about this absolute targeting property of exponential moving averages, you should bug him about it. So that's something that we can do in order to fix this oscillation problem. We can switch to either a linearly weighted moving average or an exponential moving average. There's also some data showing that there's a third class of algorithms called the harmonic weighted mean instead of the linearly weighted or constant weighted that might even outperform the exponential moving average, but don't have it programmed into the simulation. In any case, the linearly weighted, which is this orange line now, and the exponential moving average perform much better than the constant one, than the simple moving average. So let's just do a 40,000 block simulation and show how big of a difference this is and what kind of usability difference this might make. So we still see some fluctuation in, let's also add the slow one. We still see some fluctuation in difficulty. We still see fluctuations in hash rate, but the hash rate fluctuations are largest for the continuous weighted, moderate for the linearly weighted, that's the WT. The WT algorithm is actually a little bit more complicated than just a linearly weighted, but it's a good approximation. And they're lowest for the exponentially weighted ones. The fluctuations are actually, like the block-to-block fluctuations are the lowest for the slow exponential function and larger for the fast exponential function, except when there are these steps in profitability. And in those cases, the slow one responds a lot more slowly than, I think it's this right here, than the fast moving average. I've also found some instances in which the linearly weighted, at least this particular version of the linearly weighted function can do some weird stuff. It's not that bad. It's a lot better than the continuously weighted, but not perfect. So overall, my favorite is definitely the exponentially weighted moving average. We can also look at the block intervals, and we can see that the simple moving average, continuously weighted moving average, has a lot fewer blocks in the expected 600-second time frame than any of the other algorithms. It also has far more blocks at extremely high intervals. At the 1 hour interval, we get 1,000 times as many as would be predicted by a perfect adjustment algorithm, or about 6 times as many as you get from the best exponential moving average. the linearly weighted does about twice as many as the best exponential, maybe 3 times, 2.5 times, something like that. And in the confirmation graph, again, you see that the linearly weighted is a little bit higher in confirmation times than the exponential, not too bad. And the continuously weighted, the simple moving average, is much worse, 20-30 minutes. When we look at the mining strategies and the profitability for different mining strategies, we see that there's a roughly 2%, 2.5% profitability advantage for having a greedy strategy, switching as soon as it makes sense, versus having a steady strategy. Also, the oscillations seem like they might cause more blocks to be mined in a given interval than there should be. So it does seem that this simple moving average is gameable, in that like running the difficulty down very low and then mining a bunch of blocks and then bringing the difficulty back up does seem to be a viable strategy with this. With the exponential moving average, it does not seem to be a viable strategy, and we get basically the average profitability is very close to zero. The average profitability difference is very close to zero. It's very close to being fair. And the difference between the greedy strategy and the steady strategy is 0.2%. And that's true for both of the exponentials. And the linearly weighted one, or this algorithm is, the Daggerval algorithm is in between in performance. I encourage people to play around with this. We've also got a bunch of different scenarios. The FT, I believe, will modulate the timestamp, so it sends some timestamps into the future and some timestamps into the past. The pump oscillation thing will try to generate oscillations using hash rate fluctuations. Obviously, that's not necessary to generate oscillations with the CW algorithm, but the fact that it fails to, let's do it. It also fails to generate oscillations with the WTEMAs. So yeah, in pretty much all of the scenarios that we can think of, it looks like the, oops, right, I forgot. This one doesn't work over very long block intervals because it drives the exchange rate up, and that makes the equilibrium hash rate exceed the allotted 10 exahashes that we have here. So whatever, that's what's going on there. But yeah, so TLDR is that yes, the Bitcoin Cash difficulty adjustment algorithm is broken, it's messed up, it has oscillations, and this is also, like, getting a perfect difficulty adjustment algorithm is very difficult. It's really hard to get rid of these spikes and troughs, especially the troughs, without making the average like difference between optimal profitability too large. There's an inherent trade-off there to be made, and that aside, there's still a huge room for improvement. There's like a 5-fold, 10-fold room for improvement over the existing algorithm. So even though we can't make the perfect difficulty adjustment algorithm, we can still make one that's way better than what we've got, and we should. Thank you for listening, and yeah, feel free to ping me if you've got any questions, and I'll post links to these tools and also to the statistics pages, the graphs, in the comments below, or in the description below. Thanks.